This is the third video on the proof of the second isomorphism theorem for rings. And I want to start by doing a brief synopsis of what we've done in the previous videos. We've shown that because I is an ideal inside S plus I, that the quotient structure for this side of my diamond is a quotient ring. And we have also shown that since S intersect I is an ideal inside S, the quotient structure for this side of my diamond is also a full-fledged quotient ring. And the goal inside the second isomorphism theorem is to show that those two quotient rings are isomorphic. Now, in the last video, we discovered the following kinds of things. One, we want to make a note that S plus I mod I is the set of left cosets of I where the representative is actually drawn from the subring S. That was one of the things that we had to prove. And we've also defined a map phi from S plus I mod I to S mod S intersect I, given by, let's clean up my handwriting there, given by the formula phi of little s plus I is just going to be little s plus S intersect I. And in the previous video, we showed that, so in last video, we showed that phi was well defined. And in this video, we're going to show that phi is a ring homomorphism. So we now need to show that phi is a ring homomorphism. Well, let's see. In order to do that, we need to show that phi preserves ring addition. So I'm going to let it be A plus, because I don't want to deal with subscripts. So we're going to have let A plus I and B plus I be two elements of S plus I mod I. And that tells me that A and B themselves are elements of the ring S. Now look at this. If I look at phi of A plus I plus B plus I know by coset addition that that's going to be phi of A plus B plus I. And that's by the definition of coset addition. But if I'm looking at this, I know the definition of phi says that this is going to be A plus B plus the ideal S intersect I over in the ring S mod S intersect I. And so this is by the definition of phi. But we're now in the ring S mod S intersect I, and this is just a coset addition again. So this is A plus S intersect I plus B plus S intersect I. And this is again the definition of coset addition. This time it is in the ring S mod S intersect I. And lo and behold, this is just phi of A plus I, and this is phi of B plus I, so we can write this as phi of A plus I plus phi of B plus I, and that should be a coset addition. And this particular step is again by the definition of phi. And so what we've got is that phi does indeed preserve addition. So we're halfway done with showing that phi is a ring homomorphism. We now turn our attention to looking at making sure that phi preserves multiplication. So to show phi preserves ring multiplication. Now this is done in very much the same way, and I would encourage you, if you haven't already done it, to stop the video, try and do this one on your own, and then start the video and compare your answer to mine. So again, we're going to let a plus I and b plus I be any two elements of s plus I mod I, and that does tell me that a and b both belong to s. And now look at this. Phi of a plus I times b plus I is just going to be phi of AB. Let me make that symbol a little bit clearer. Plus I. And that's by the definition of coset multiplication in the ring S plus I mod I. But I know what phi does. Phi takes this coset here to the coset AB, and again my B didn't turn out very well, so let's make that clearer. Phi of AB plus I is AB plus S intersect I, and that's by the definition of our map phi. But this is a coset product in the ring S mod S intersect I, and so I can write it as A plus S intersect I times B plus S intersect I, and this is by the definition of coset multiplication in the ring S mod S intersect I. But this particular thing here is just phi of A plus I, and this is phi of B plus I, so we wind up saying that this is phi of A plus I times phi of, let's see, I forgot to write that down, so let me correct my notation again. Phi of B plus I, and I know this by the definition of phi. And if I put all of this together, we can conclude that phi preserves ring multiplication as well as ring addition. And that's enough to say that phi is indeed a ring homomorphism. So phi is a ring homomorphism. In the next video, we will look at proving that phi is a ring isomorphism by proving that phi is both onto and one-to-one.